Yeah, now coming to the next step, that sizing of section. Sizing of section. Now these are the formulas which you don't understand immediately. Yeah, we'll give you the reference for this in bit later cases. So now this is the formula to calculate the bending capacity of a section. This is the formula used to calculate the bending moment capacity of an I section, which says MD is equal to beta B into ZP. ZP stands for plastic section modulus. ZP stands for plastic section modulus into Fy by gamma m naught. So now this is the very basic formula derived from your bending equation, that is M by I is equal to sigma by Y is equal to E by R. So now assuming for timing, assuming this as 1, beta B as 1, we have to calculate what is ZP required. Now ZP required, assuming for time being, assuming beta B as 1, now ZP required will be, so MD divided by Fy by gamma m naught, rearranging this formula. So ZP required will be MD divided by Fy by gamma m naught. Now MD, that is design bending moment, we know, which is 449. So that is 449.59 into 10 to the power 6 to convert into Newton millimeter. The bending moment has to be kilonewton meter. Yeah, now this 10 to the power 6 is multiplied to convert it to Newton millimeter divided by Fy by gamma m naught. Fy, it is yield strength 250 Newton per square mm. Gamma m naught is 1.1. So now you are getting ZP, that is plastic section modulus. Plastic section modulus, which is 1.978 into 10 to the power 6. Now we have to go to IS 800 page number 138 to find an I section. To find an I section having plastic section modulus at least equal to this or greater than this. Now we'll quickly go there. Yeah, page number 138. Yeah, here you can see plastic section modulus. So the plastic section modulus as per the requirement is 1.978 into 10 to the power 6 cubic mm. So now we have adopted is ISMB 550. Directly we'll go to the same section. ISMB 550. Yeah, for ISMB 550, 1, 2, 3, 4, 5, 6. From the top sixth one, now I am referring to the plastic section modulus. From top sixth one, 1, 2, 3, 4, 5, 6. 6, that is the ZP of this ISMB 550 is 2711.98 cubic centimeter. 2711.98 cubic centimeter. So if we convert that to ISMB 550, sorry, here is the 2711.98. Yeah, here is the ZP, plastic section modulus. There is a big difference here. This is elastic section modulus and this is plastic section modulus. So we should be taking plastic section modulus. Yeah. Now, a small mistake here. Yeah, he has rounded off the figure. It is 2711.98, which is rounded off to 2.712 into 10 to the power 6 cubic mm. So there it was given as cubic centimeter. Here it is given as cubic centimeter. So now while noting down, this is converted to cubic mm. Yeah, and also you should note down your IXX or IZZ from the steel table. Now IXX and IZZ are not given in the IS 800. Now, this value is also essential and has to be noted down from the steel table. Yeah. Now in the third step, what we have done, we have size the section using the basic bending equation formula. We have adopted what is the size of I section should be used for the design. We have adopted ISMB 550. Now you should also note down all the cross-sectional properties also. The breadth of the flange 190 mm BF, thickness of the flange 19.3 mm, thickness of the web 11.2 mm, and overall depth which is 550 mm. So next step is section classification. Now for section classification, you have to go to table number 2, page number 18 of IS 800. For section classification, you have to go to table number 2, page number 18 of IS 800. Now quickly we'll do that. Page number 18. Yeah. So page number 18 and table number 2. When you refer here, there are few ratios you have to check. The first ratio is B by TF. The first ratio is B by TF. Now B refers to, so you have to refer to the figure here. In the next page, page number 19, B refers to half of the flange. You can see here B refers to what? Half of the flange. Now we know flange width is 190. So B will be 190 by 2. 190 by 2. B is half of the flange, 190 by 2. TF refers to thickness of the flange. Now that is already noted down. Thickness of flange is 19.3. 19.3. Yeah. So now that ratio, when you calculate, so you will be getting as 4.92. You will be getting as 4.92. So now again going back to the table number 2 there. Yeah. So now we should be referring to what? Yeah, the first row, outstanding element of a compression flange. Outstanding element of a compression flange. So within that there are two clauses, rolled section and welded section. Now what we have considered is a rolled I section. So we should consider the first row again. So there it says a ratio of B by TF. There it says a ratio of B by TF. Yeah. Now this, which is already we have got it as per the calculation, we have got it as 4.92. If this ratio B by TF, if it is less than 9.4, your section, your flange is classified as plastic. If it is greater than 9.4 and less than 10.5, it is classified as compact. It is greater than 10.5 and less than 15.7, it is classified as semi-compact. And if it is greater than 15.7, it is classified as slender. So in our case, it is 4.92. So 4.92 in the sense, yeah, B by TF 4.92. It is less than 9.4. It is less than 9.4. Therefore, flange is classified as plastic. If this value was 10, if this B by TF was 10, that value would have been greater than 9.4 and less than 10.5. In that case, your flange will be classified as compact section. So now in this case, it is 4.92, which is less than 9.4, which is less than 9.4. Hence, flange is classified as plastic section. So now that is what is written here. Flange is plastic section. Yeah. Next calculation you have to do is the D by TW. D by TW. Now D by TW is nothing but depth of the web divided by thickness of the web. Now how do you calculate depth of the web? This is web. How do you calculate depth of the web? That is overall thickness minus thickness of the top flange and thickness of the bottom flange. That is overall thickness, that is 550 minus thickness of the top flange and thickness of the bottom flange. That is 550 minus top flange is 19.3 and bottom flange is 19.3. Whole divided by TW stands for thickness of web, 11.2. That is 11.2. So now which will work out as 45.66. Which will work out as 45.66. Now again going back to, yeah, now that D by TW is shown here. D by TW, D stands for what? Depth of the web. D stands for depth of the web and TW stands for thickness of the web. Depth of the web and thickness of the web. Okay, now coming back to the problem. Yeah, so now which will work out as 45.66. Yeah, now going back to IS 800. Yeah, so now for that you have to refer to web of an I section. Web of an I. So now for this we have three sub rows, that is neutral axis at mid depth and general and axis of compression, axial compression. Now again in that you have to refer to the first row. Since it is a symmetric axis, neutral axis will be at the mid depth. So now for that D by TW, so we have is how much? 45.66. Now that 45.66 is less than 84. Yeah, is less than 84. 84. So now, since this 45.6 d by tw is less than 84, hence web is also classified as plastic. If this d by tw is greater than 84, and less than 105, say 100. If this d by tw is say 100, so it means greater than 84 and less than 105, then web would have been classified as compact. Greater than 105 and less than 126, say 120, which is greater than 105 and less than 126, so that will be classified as semi-compact, and anything greater than 126 will be classified as slender. Now in this case it is 45.66 less than 84, hence it will be classified as plastic. Yeah, we have written as web is plastic. Yeah. So now both flange is also plastic and web is also plastic. Now entire section can be called as plastic section. Since flange is also plastic and web is also plastic, the entire section can be called as plastic section.